So lastly, we're going to look at the band pass and conversely the band reject filters. You'll notice to the right there, the curves look a little different from what you've seen before. You've got essentially the low pass and the high pass filter curves butted like bookends up next to each other. And you can see we have a lower cutoff frequency and an upper cutoff frequency. So what we're doing is we're creating a tuned circuit that only passes high pass or low pass signals. Or you could get a notch situation where we are doing a reject on this. So bandpass filters are filters that pass only a band of frequencies. So if we wanted to chop off the high frequencies, chop off the low frequencies, and only do the mid frequencies, this is how we could do it. This type of filter rejects both of those types of frequencies, high and low, but passes the range of frequencies in between. So the curve has two cutoff frequencies. F1 is the lower cutoff frequency. F2 is the upper frequency. So again, we're going to look at a specific circuit here that we're going to dissect a little bit and understand how the circuit works to do that job exactly. So at low frequencies, the capacitive reactances will be quite large compared to circuit resistances because in this case C2 is connected in parallel to its high reactance or low susceptance will have a negligible effect. So if you look back over here, there is C2. You can see it's hanging on the output of the circuit. We've already simplified it here by removing C2. Okay, so they're saying that the effects of C2 will be negligible. Because C2 is connected in parallel, its high frequencies reactance will have a negligible effect. So C1 then is connected in series, resulting in a low output voltage at low frequencies. So again, we're going to take a look at Theveninizing the circuit to make it easier to do the analysis. By Thevenin's equivalent, Theveninizing the circuit, we're going to open C2, which has a little effect then at the low frequency. So you can see at the output there, the C2 is now gone because in essence, we've clipped it out of the circuit. And the output then now is taken across R2. Then we're going to Thevenize C1 at F1 such that the capacitive reactance equals R Thevenin. So to calculate the F1 cutoff frequency, if you will, the knee, we have 1 over 2 pi R Thevenin times the C1. So you can see here in the middle description here, then we have R Thevenin is equal to R1 and R2 summed together. At high frequencies, we can ignore the low reactance of C1. The low reactance of C2 then causes a reduction in the output voltage then at high frequencies. We're interested in the relationship, again, between the reactance of C2 and the resistance that C2 sees. Okay, remember what's going on here when the capacitor starts sensing these frequencies, it starts to change its reactance. By Nortonizing the circuit, then we can solve for G Norton in the equivalent circuit from R1 and R2 in parallel. So the Norton's equivalent circuit then becomes the point where G Norton is equal to the susceptance of the capacitor. And here's our relationship, G Norton divided by 2 pi C2. Okay, so now we end up with a high frequency circuit. Notice here we've got, again, like I said, we've got a current source replaced from the voltage source in our circuit. So we've got the current source and G Norton. It becomes our equivalent circuit. In the mid-frequency range, we ignore the effects of both capacitors. The reactance of C1 is negligible compared to R Thevenin times the product of R1 and R2. And the susceptance of C2 is negligible compared to the conductance Norton G1 plus G2. The mid-frequency circuit then in essence becomes R1 and R2. Even though we consider that the circuit passes passes a band or a range of frequencies, a middle frequency F sub m could be calculated by taking the square root of the product of F1 and F2, the cutoffs. So in looking at an example here, we've got values given. Again, we go back to our original circuit, typical circuit that might be part of an output for an amplifier. R1 is equal to 2 k ohms, R2 3 k ohms, C1 1 microfarad, C2 500 picofarads, and a source of 20 volts. So they want us to look for F1, F2, V out at the mid frequencies, and V out at the cutoff. Okay. So again, we start with the relationships we were given. F sub 1, R Thevenin then becomes R1 plus R2, or 5 k ohms. So we can use that 5 k ohms then in our relationship for solving for F1, R Thevenin, and C1. So we've got 31.8 hertz for the first cutoff frequency. Then we solve for the second cutoff frequency using the Norton's equivalence of conductance divided by 2 pi of capacitor 2. Okay, so the first thing we need to do is calculate G Norton. So G Norton then becomes the sum of the two conductances, G1 and G2, which gives us 833 microsiemens. F sub 2 then equals the quotient, G Norton divided by 2 pi C2, and we get a cutoff frequency of 265 k ohms. Okay, so you can see there's quite a range there, from 31.8 hertz out to 265,000 hertz. Okay, so at the cutoff, or at the band of frequencies F sub m, the effects of C1 and C2 are negligible, so we treat them as a simple circuit where we only have the resistors, so we can treat it like a simple voltage divider, where the output is taken across now R2, because C1 and C2 are in essence negligible. That just means that their resistance is gone. So we end up with an output voltage of 12 volts based on the values that we were given. At F1 and 2, the phase angle is 45 degrees. That's a given. At these frequencies, the output then becomes 0.707 times the max output voltage. So V0 max is the output voltage in the mid-frequency range. V out then at F1 equals V sub 0, and at F2 we equal 12. Okay, so times 0.707, or 8.49 volts. Okay, so to find the two cutoff frequencies, F1 and F2, ignoring again C2 and C1, and treating C1 though as a load, we can determine the value of F1. So in this case, you can see we've shorted out the C1, so it just becomes the R Thevenin value, R3 plus R1 and R2 in parallel, and that gives us our R Thevenin C1 relationship for calculating F sub 1 at 30.4 hertz. Treating C1 then as a short circuit, and assuming that C2 is the load, we can determine the value of F2. Again, we calculate for G Norton, find the conductance for the three resistors. We get 2.05 millisiemens, and we can solve for F sub 2. Norton's conductance divided by 2 pi C2 gives us 163 kilohertz. So now the bandpass circuit using an inductor, a capacitor, and a resistor can be calculated to determine what the bandpass would look like. So you'll recall that the resonant frequency F sub r is at the point where X sub L and X sub C are equal. Remember, when they go into resonance, what we in essence have is the energy being swapped back and forth between the capacitor and the inductor. and they, in essence, they nullify each other. So as we increase the frequency above resonance, x sub c increases, x sub l decreases. Eventually, we reach a frequency where the difference between x sub c and x sub l, it leaves us just r. So it equals r. So this is the upper cutoff frequency, f sub 2. So in an RLC circuit, the range of frequencies between F1 and F2 then becomes the bandwidth. And so we have these relationships that we can then use to calculate the bandwidth and the cutoff frequencies. And we'll see those. We're going to use them. Bandpass or band reject filters then are usually designed to be very selective. We either want to pass certain frequencies or we want to restrict certain frequencies. So they're designed to pass a narrow band of frequencies. The highest quality features have the narrowest band. And something you're going to learn later is you want to have those bands be as instantaneous as possible. You don't want to have a long slope on them. You would like them to change very quickly. And when you get into your follow-on courses, you will see that. This selectivity characteristic is called the Q and is defined as the ratio of the resonant frequency to the overall bandwidth. So let's take a look at using those relationships. If we have a simple RLC circuit where the input voltage is 3 volts, the resistance is 100 ohms, the resonant frequency is 1 kHz, and we have a Q or quality of 20. Find the bandwidth, F1, F2, I max, P max, and the voltage across the resistor at resonance, and VR, I, and P, the power at F1 and F2. So looking at our relationships, we haven't used these before, so we're going to go ahead and implement them. Q, as I said, is the ratio of the resonant frequency to the bandwidth. We can move these terms around then to solve for the bandwidth from the Q, since we were given Q and the resonant frequency. 1 kHz over 20 gives us a bandwidth of 20 Hz. So we've got a pretty narrow bandwidth. So F1 is solved by taking the resonant frequency minus the bandwidth, half of the bandwidth, and we get 975 Hz. F2 is the resonant frequency plus half of the bandwidth, we get 1025 Hz. So you can see this is the points of our cutoffs, and we've got a very narrow bandwidth of 50 Hz. Okay, so we've calculated on either side of the center frequency. So V sub R equals V in, 3 volts at the resonant frequency. At other frequencies, then V sub R would be less than 3 volts. So the maximum current then, V sub R by R, gives us 30 milliamps. The maximum power then, V sub R by I, gives us 90 milliwatts. So if F1 at an angle of minus 45 and F2 at an angle of 45, then we have either F1 or F2. Okay, so we can calculate the voltage across the resistance then, 2.12 volts. The current, V sub R over R, gives us 21.2 milliamps. And the power, then the voltage times, the current times the voltage through the resistor. The sum of the product of those two gives us 45 milliwatts. In another example here, let's look at calculating for the bandwidth in the Q given the inductor, capacitor, and the resistor values, 40 millihenries, 200 nanofarads, and 30 ohms. Okay, they also want us to calculate the frequencies, the resonant and the 2 cutoffs. So the resonant frequency is equal to 1 over 2 pi times the square root of LC, which gives us 1.78 kilohertz. The Q for the circuit then, X sub L over R, is equal to 2 pi, the resonant frequency times L divided by R, or a Q of 14.9. The bandwidth then can be calculated from the Q and the resonant frequency, gives us 119 kilohertz. And then our 2 cutoff frequencies, the resonant frequency plus and minus half of the bandwidth, gives us 1.72 kilohertz and 1.84 kilohertz. So now we've looked at all of the parameters for a bandpass filter. Finally, we look at just an example here of a band reject filter. You can see we've got a little different configuration here. We've got the capacitor and the inductor in parallel now with the resistor in series, and you notice that the output curve looks a little different. It's inverted from what we've seen. The parallel LC circuit offers a maximum impedance at the circuit to the circuit at resonance. The circuit current and V out then is a minimum, and the frequencies between the two cutoffs then become rejected.